I want to say welcome to everyone joining us in this session. I'm Nezih Soydan from Lean Institute, Turkey. Our speaker, Ferhat Topal, is working as supply chain director of FAF VANA. He will share with us their intense efforts to create a unique system for managing their supply chains by developing production and supply planning methods with lean approaches tailored to their needs. Yes, Ferhat, we are ready to hear from you.
Thank you. I would like to start by giving a warm welcome to everyone joining us at the Lean Global Connection. Today, I will be sharing our project called a Global Production and Supply Planning Model built on Lean principles. I will also talk about the key experiences and lessons we have learned along the way. I want to take a moment to thank the Lean Institute Turkey for giving us this opportunity to present our work. As we all know, many of us face similar challenges within our supply chains. In a world that's always changing, we need to create solutions that help us stay resilient and flexible by applying common and consistent methods and processes. In this presentation, I will give you an overview of the main findings and insights from the studies we have carried out with this approach. Before moving into presentation, let me briefly share its outline. Today, I will provide an overview of the organization structure of FAF Group, our supply and inventory management methods, the before and after of our requirement calculation models built on Lean principles, and finally, the calculation models for finished goods, semi-finished goods, and raw material requirements. As you can see on the slide, we are a Turkey-based global valve manufacturer and supplier with 39 years of experience. We serve our customers with our design engineering, manufacturing, and testing capabilities. First, let me quickly introduce FAF Group. FAF Group is a global structure composed of 4 companies: FAF 5, FAF Casting, FAF China, and FAF Russia. While developing the models, we will discuss today one of our most critical challenges was managing the complexity of this global supply network. Therefore, before explaining the modeling process, I would like to give you a brief overview of our current supply system and production diversity. Finished goods. In our industry, customers expect the products they request to be delivered directly from stock. For this reason, we deliver more than 250 different products from stock and operate with a pool system. We have substitute products that are either manufactured at FAF 5 or supplied from our FAF China facility. Semi-finished products, our factory operates 27 different processes, 23 of which can serve as both initial and intermediate processes. In addition, we have several outsourced processes. Production takes place along more than 350 different routing paths. Due to this structure, cell-based manufacturing is not feasible in our environment. Some key data: average operation time, 7 minutes. Average number of routing operations, 4. All this diversity makes production planning one of our core processes. Inventory structure. Our inventory includes semi-finished parts, 100% produced in FAF 5. Semi-finished parts partially produced in FAF 5 and partially sourced from FAF China. And some items supplied from FAF China, but also can be produced in Turkey when required. Commercial goods. which are stocked in both China and Turkey warehouses. However, managing not only warehouse inventories, but also monitoring goods in transit, especially those on the ocean, is a critical issue for us. Before diving into the details of the lean-based models we have developed, I would like to explain the infrastructure preparations we made and the challenges we faced before modeling. At FAF, we currently manage 19 different supply methods. To standardize such a wide and complex structure, design a lean system, and make it sustainable on a global scale, we conducted a comprehensive analytic process. Now, I will share that process and the key challenges we encountered step by step. When explaining our modeling process, I would like to divide its development into 3 consecutive phases. Phase before ERP revision. During this period, we were unable to monitor sales orders, purchase orders, work orders, and stock levels simultaneously. We could only align the data at the end of each day, once all manual data enters had been completed. Therefore, I can easily describe this phase as our dark period. We could not access real-time data, which made decision-making extremely difficult. After ERP and MES integration, in this period, we start using the MRP, Material Requirement Planning System, actively. Thanks to the ERP MES integration, we were now able to manage data in real time. We could create assembly plans and, based on these, generate semi-finished and raw material plans. The planning visuals you will see on the screen summarize the level we had reached during this phase. Although this was a significant improvement, it was still far from being optimal. And in the next section, I will explain why in detail. During this phase, we successfully standardized and systematized several key planning activities like defining lot sizes, setting assembly days and assembly lines for each product, establishing interdepartmental communication and add-on systems, integrated the assembly plan with the ERP system, linking semi-finished production plans and raw material procurement plans directly to the assembly plan. However, despite all this systematization, some fundamental issues still persisted. The first major issue we faced was the difficulty in achieving balanced assembly planning. This often resulted in either idle capacity on some assembly lines or overtime work on others. For make-to-stock products, we would use a variable time, fixed quantity production model. When stock levels fell below the minimum threshold, the system automatically triggered production to restock to the maximum stock level. For make-to-order products, we followed MRP-generated production suggestions. However, this approach had some significant side effects: non-optimized lot sizes for semi-finished products, very high stock levels, increasing supply chain complexity, which made problem solving more difficult. Additionally, we observed fluctuation workloads at supplier facilities, a classic bullwhip effect. Demand volatility across similar products often resulted in delivery delays. Another important challenge was managing substitute product inventories. Since we could not manage these inventories in an integrated manner, one item could fall into a stock shortage, while another remained at a high stock level. Finally, production bottlenecks and supply delays extended our overall lead times. All these issues clearly demonstrated the need to evolve our system into a leaner model-based structure that could perform requirement calculations aligned with each supply method. At this point, we initiated the lean production and supply planning project and began implementing requirement calculation models based on lean principle. We shifted to a structure where centralized calculation models were developed for different supply methods. During this phase, we achieved making process standard, optimization of inventory levels, clear definitions for production and procurement quantities and periods, and full integration of all models with our ERP system. Today, we operate with a structure that is data-driven, lean, and sustainable. In the next section, I will share the details of our finished and semi-finished products requirement calculation models implemented during this new lean phase. As a first step, we conducted a Pareto analysis to identify which products represented 80% of our total production volume. Then, using ABC XYZ analysis, we classified these products based on their sales quantity and demand fluctuation. This approach allows us to clearly define which products should be included in detailed planning. For the remaining items, we continue to use our standard MRP system for make-to-order planning. As a result, we started planning approximately 80% of our total annual production. For finished goods production, we evaluate three different planning methods: variable time, variable quantity production, variable time, fixed quantity production, fixed time, fixed quantity production. After extensive simulations, we determined that the fixed time, fixed quantity production method was the most appropriate approach for our base planning model. However, due to seasonal fluctuation and periodic variation in sales orders, we realized that we needed the flexibility to adjust in lot sizes when necessary. Therefore, the model was designed to execute routine production on schedule, while also being able to automatically adjust lot sizes whenever required. Now, let's take a closer look at how the model decides when to make change in production lot size. Lead time period, we decided on 4 weeks. Cycle time, we set it at 4 or 8 weeks per product. Logic of the model, we take into account the quantity to be added to inventory within the lead time, as well as the quantity of sales orders to be delivered within the cycle time. Decision checkpoint, we check this question to judge on lot size. Does the inventory level at T+4 exceed the maximum stock level and fall below minimum stock at T+8? Our objective was to maintain stable lot size across each 4-week period with minimal iteration. This calculation method is applied to all products included in the lean model. I want to present you a sample case to show how the system calculate and decide on production lot sizes. We predefined min and max inventory levels for each stock units. On the table and graph, you can see how the lot sizes are determined and inventory level is fluctuated. Simulation results show that despite demand fluctuations, the system required only one adjustment to the lot size over 8 cycles. When we run this model across all products, we can see exactly how many units of each product should be produced in each 4-week period, which enable us to establish a balanced assembly plan. We trigger production weekly, determining which products will be produced in which week of the 4 or 8-week cycle. However, there is another key factor. We need to group products based on their common material consumption and then determine the production weeks for each group to achieve both balanced assembly, Heijunka, and balanced production load. In the chart shown on the screen, the left-hand side lists finished product codes, while the columns indicate the semi-finish consumed by each product. We use group technology method for grouping finished goods. These products should be scheduled in the same week for planning and assemble 4 weeks later. Keep the same week alignment. Once the grouping was complete, we determined which groups will be assembled in which weeks. When we examine a 12-week period, you can see on the screen the distribution of product groups across the weeks, along with the assembly lines and production workload. The primary objective here was to optimize the workload distribution of assembly lines while simultaneously balancing the load of production work centers. The model even determines work order numbers automatically, which are then transferred into our ERP system. As work orders are executed and consumed, the MES system feeds data into ERP, and the ERP system simultaneously updates our lean model, certain a full synchronized digital planning cycle. We are using this system for about a year, and it will summarize our achievements. We have now a balanced assembly and production plan. Overtime work is reduced by 61%. Inventory loss is reduced by 32% on average. Our planning and operational efficiency are improved. We have designed the finished products and semi-finished products requirement calculation models to work in an integrated way. This integration allows us to have a more reliable and coordinated planning process, ensuring that both production and procurement are fully aligned. Within this model, we calculate both Heijunka and non-Heijunka consumptions. A semi-finished products pool system has been established, ensuring production in line with non-Heijunka consumption plus Heijunka quantity. Some semi-finished products are partially produced in-house and partially produced externally. The model determines exactly how much should be produced and how much should be purchased. If there is any change in purchasing lead times, the production quantities are adjusted according to the week in which consumption will take place. Using the finished production requirement calculation model, we can determine how much of each semi-finished products should be produced in each period. When products not included in the model are produced, they consume some common semi-finished components. These quantities must be kept available in the supermarket area, buffer stock to ensure continuity of production. In some cases, a certain percentage of semi-finished products is produced locally, while the remaining percentage is supplied from our FAF China facility. For these products, it is essential to calculate what portion of the requirement will be produced and what portion will be sourced externally. The required quantity for semi-finished goods is calculated as shown on the slide. If there is no difference in the number of wipes to be assembled between the two periods, we calculate the required quantity based on consumption. If there is a difference, the difference is included in the calculation. We can observe the movements of semi-finished products stock level on the table and diagram. On the previous 4 weeks, the consumption is based on make-to-order production of finished goods that are not included in the Heijunka model. And on the last period, we see the amount consumed and the amount produced for Heijunka products. After calculating the amount required, we decided whether to produce all domestically or partially and order the remaining to FAF China. As a rule, we fix the amount and period to be ordered to China as long as the stock is between predefined levels. We handle the variation in domestic production. By the implementation of this planning approach for semi-finished goods, we achieved a balanced weekly workload for semi-finished goods at paint shop, machining, and welding operation. This was due to fixed production periods and amounts for finished goods as much as possible. On the other hand, with a fixed 4-week period for production, we optimize lot sizes and efficiency increased and inventories are kept at a minimum level. Now, let's talk about raw material procurement system. Previously, we determined areas for improvement. One of them was early procurement of materials, because MRP calculates how much is needed, but not when it's needed. The lead time defined in MRP were not realistic. Due to high variability of orders, our suppliers were not able to respond to them as required. The other problem was high inventory levels. Early purchases led to excessive stock levels. And finally, materials with more than 90 days of lead time could not flow smoothly. Lack of a periodic procurement system was the reason. While defining the requirement calculation method for raw materials, we decided to use 3 different methods. We standardized box types and quantities per box for each material. Defined and agreed on MOQ and lead times with our supplier, while promising to give order with minimum fluctuation in periods and amounts, and demanding a 100% on time delivery. We run the model daily for the procurement items we purchase from Turkey. Each day, different items are calculated. Example, fastener on Monday, ceiling elements on Tuesday. With purchase request create accordingly, we calculate and order overseas procurement items at defined periods. The defined periods ensure continuous material flow. If a supplier's minimum order quantity is higher than our period requirement, we trigger the purchase order after consumption reaches the minimum order quantity. I would like to share our raw material requirement calculation model with you, followed by a chart showing the inventory movements of one of our items. Before implementing the model, the stock level of this item had reached 23,000. After the model was put into operation, the stock was reduced to below 5,000. Following this, stock levels began to fluctuate within the set limits, ensuring that they did not exceed 5,000 based on consumption and procurement activities. Finally, I can summarize what we achieved by implementing these methods that I try to explain in this presentation. Now we have a system that works in real time and with reliable calculation system and optimized result through ERP, MES, and lean model integration. A balanced assembly and production plan at a global scale. Semi-finished goods production and procurement are done with optimized lot sizes. Management of commercial goods and raw material flows smoothly. Commercial goods and raw materials per market with optimized stock levels. Global inventory management is achieved. Final words about our approach. It is difficult to compete with China in production in terms of cost. But we have a strategic advantage in Turkey as being close to markets where we can flexibly respond to customer demands. If we decided to shift the whole production to China, perhaps this could bring us a financial advantage, but lack of flexibility as well. On the other hand, if we were decided to produce everything in Turkey, we could lose our price competitiveness. So, the best decision was to use a mixed model by lowering our production cost by shifting some of our production to our China plants, but managing the variability and the request of our customer for flexibility, fast response time, and for shorter lead times from order to delivery, by keeping the production in Turkey as well. The result of using this mixed model brought a complexity in managing the supply chain, but by using a lean approach, we could finally find a way to handle it by designing a model that fits our needs, not by just copy a simple pull system. Thanks for your participation and good luck in your efforts to be leaner. Thank you.
Thank you, Ferhat. It's really a difficult job to combine all these different strategies and methods like make or buy decisions, where to make decisions in Turkey or China in this case, whether make to stock or make to order, where to stock and how much, and all these decisions apply to raw materials, semi-finished goods, and finished goods. Really a good job. Thanks for sharing and thanks for listening to everyone. Our time is over now and say goodbye to everyone. Thank you.
Thank you.